Hello everyone. So now we are going to start chapter 13. So 13.1 is all about vector functions and space curves. So firstly, before I give you the definition, I want to show you the graph. What's the meaning of vector functions? Now let's have a quick review. What is a vector? So before we know the vector, if the vector, for example, given by 1, 2, 3, for example, and the point is 1, 2, 3, and the vector from the origin O to the point P, this is just the vector, right? So we can say the vector equals this, and is also OP vector. So here the point P and X, Y, Z. Now let's take a look. We are going to have a vector also, but this vector is a function of t. So let's see, x, y, z. Right now, we also have a vector. The vector is given by rt. Okay, rt. So it's going to be a variable of t. Now let's take a look. The point is given by, it's not like a constant number. It's going to be ft, gt, ht. So it's like the point is a variable of t. Okay, x, y, z can be changed when t change. So it's something like kind of like x equals ft, y equals gt, z equals ht. Okay, and we can take a look. So when t change, our rt definitely change. Sometimes, for example, it may give us just like a curve. Okay, so when t equals 0, it may start at the beginning at here, and then when t goes, it's like give us a curve. And this is called the space curve, okay, given by the vector function. And the vector here is called a vector function. So you can think about this. It's like a particle move during the time interval, okay? Moves during a time interval. So later we're going to see a lot of examples. So here just a basic idea of vector function. Now let's take a look at the definition. Right now we have f equals xt. Okay, so all the components, they are the function of t, and z equals ht, and the t is in some interval, okay, interval I. So let's say when a particle moves through space during a time interval I, okay. Then we think the particle's coordinate as a function defined on I, okay, so let's see. Then the points which is given by those functions ft, gt, ht makes up the curve. And the curve definitely is in 3D, right? 3 dimensional, because here we have 3 components. So curve in space, that we call the path. Okay, and the equation parametrize the curve. Those equations, they are like a parametric equation. You can also think about the line. Okay, the easiest one is the line equation. For example, -2 minus 3t, z equals 5 plus t. So we know this is a line equation, right? And this is line pass through the point 1, -2, 5 with some certain direction. So actually this is a line. It's also a curve in space. Okay. And we call this vector function. And now let's see, we're going to write down this way. RT, okay, write down this as a function. Before we just write down the vector as V, vector R, but here we write RT. RT equals what? Equals OP vector. And which is FTI if we write down in IJK form, and GTJ HTK. And actually this is same as the component form, right? FT, GT, HT. So we can write down either way. And here the point XYZ, which is the point actually given by FT, GT, HT, is the particle's position vector. Because when we give a t value, so we know where's the point. So for certain t, we know the certain position. So this is called particle position vector. Here the function f, g, h, we call them component function, and sometimes we just call them components. Now let's take a look at the first example, and we're going to see the vector function. What's the vector function look like? The first one, graph the vector function, and the vector function is given by this one, RT. So you can see we need to be familiar with this kind of thing, RT, and here the first component is cosine t, okay, second sine t, and t. All sum is made given by this way, I sine tj and tk. So they are the same thing, right? Same. Okay. Now let's sketch the graph of this one. So what's the meaning of that one? Firstly, let's take a look. That means x is cosine t, and y equals what? Sine t, and z equals t, right? So when we translate this vector, and we know x, y, z equals those three things, and think about the polar. So x equals cosine t, y equals sine t. What's the meaning of that one? So in plane, this is like a polar coordinate, right? So what's the meaning of that? That means in xy plane, so right now we just don't think about z, just think about, you can think of when z equals 0. So xy means what? Xy should be a circle, satisfy a circle, right? X squared plus y squared equals 1, okay? So we know in xy plane, this is a circle. And z, if z can be anything, so it's kind of like cylindrical, like this one. But right now, z equals t, so when you can think about this way. So when z equals 0, if we say z equals 0, okay, so when t equals 0, z equals 0, right? And also, where's the point? We can say x should be 1 because it's cosine 0, which is 1, and y is sine 0, so it's going to be here. The point is going to be here, okay? So this is like the start point. And then when t goes up, but you know x, y always need to satisfy circle, so that means the point has to be on the cylinder. Okay, cylinder. So it has to be on cylinder. So how does this particle move? So it's going to move like this way. So when t goes up, okay, but it has to keep on the curve, on the cylinder. So something like this. So let's give us the path, okay, of this vector function. And here is initial point, like when t equals 0. And there's a name for this curve. This curve is called helix. Okay. The curve rises as. Now we can look at some exercise problem. So let's take a look at this one. If our curve looks like this, sine pi t and cosine pi t. Okay. So firstly, from this RT vector function, we know this vector should be in 2D already. So do you know 2D already? So here we know it has two components, so definitely it's in 2D, it's in plane, right? Okay, we know in plane. So we don't have z here, we just have x and y. And whenever we have sine, cosine thing, you know, they have a property. So sine square pi t plus cosine square pi t equals the identity, which is 1. So that means x squared plus y squared equals 1. So that means it is a circle in plane. So graph is here. And the radius definitely is 1. Now let's take a look at the second one. The second exercise problem, RT equals 2 cosine t plus 2i plus 2 sine tj plus k. Okay, so what's the meaning of that one? So I also like to translate this into x equals 2 cosine t and y equals 2 sine t and z equals what? Z is, if x squared plus y squared equals 4, that means it's a circle in plane with radius 2. So now we draw this graph. Okay, definitely we know this vector function is in 3D because it has 3 components. So x, y, z. And on xy plane, that's a circle with radius 2. And right now, if z can be anything, so xy has to be satisfied on the circle. So z can be anything, it's going to be a cylinder, right? But right now, look at our last component, z equals 1. So if we say here is 1, so that means x, y satisfy the circle and z has to be 1. So actually, what's the graph for this curve? Is here. Okay, so that's another exercise problem. Now let's take a look at the limit and the continuity for vector function. Because it's function, it's a vector, but it's also a function. We treat it as a function. So for the function, we have limit. So let's see. Limit and the continuity. So we just look at the limit. Continuity, we don't use this too much. So let's take a look at definition 2. The limit of vector function and the function is given by RT, so it's defined by this way. Just by taking the limit of its component functions. So let's take a look. If RT equals xt, yt, zt, okay, then the limit of the, when t goes to some number, so we say a, the RT function, we just take the limit of each one component function. So here x goes to a, and the second component limit x goes to a, yt, and the limit zt, t goes to a. Okay, so pretty easy. Now we can take a look at the example. If our RT equals cosine t, sine t, the helix, okay, right. What's the limit when t goes to power 4? So let's take a look. So when t goes to power 4, we just take the limit of each one. So t goes to power 4, cosine t, that's the first component. So I'm going to write down the component way, okay, cosine t. And the second component, t goes to power 4, sine t, right? And the last one, t goes to power 4, okay? And evaluate this. So cosine power 4 is root 2 over 2. Sine power 4, root 2 over 2. And t just goes to power 4. So that's the limit. Pretty easy. Let's take a look at this one. If RT is given by 1 plus t cubed I, t e to the negative tj, sine t over tk. Okay, we are going to find limit t goes to 0, what is RT? I'm going to give the solution here. the only thing I need to say is the second term. Okay, this one is commonly used the limit. This goes to 1. Or you can use L'Hopital's rule. So let's take a look at the limit of our second component, t times e to the negative t. So firstly, we change this into t over e to the t. And next, we can use L'Hopital's rule. So which is the limit, because the top bottom function both go to 0, so this is 0 over 0 type actually. So we just take the derivative of each one. So derivative of t is 1, and here's e to the t. And e to the 0 goes to what? E to the 0 is 1, right? So the limit is 1. The answer for this problem is RT, which is just 1. Okay, second component goes to 1. The last component also goes to 1. So here is the limit. Let's take a look at example 3. So example 3, the curve is given. We are going to find the vector function. So let's see. If the curve is a line segment, so find a vector equation for the line segment. That join 2 points. And the points are P1, P and Q. P, which is 1, 3, negative 2. 2 point Q, which is 2, negative 1, 3. Actually, we did a similar thing in our second midterm. What we did, we found the parametric equation actually, right? Parametric equation in 2D. So our point is just like a 2D point. Here is 3D, but the idea are totally same thing. Now let's take a look. So if here we have P, we have Q, 2 points, and we're going to find the line segment drawing those two. Same thing, we want to find the PQ vector. So the PQ vector, we use the terminal point minus initial point. 2 minus 1, 1. Negative 1 minus 3, negative 4. 3 minus negative 2, so should be plus 2, 5. That's PQ vector. And we can treat this as V vector. And if we pick the point P, so we can write down the line equation. Right? Okay. So x equals what? X naught, which is 1, plus TV1, so which is t, because this is just like a V vector, the direction of the line. And y equals y naught, which is 3. So here we pick the point P. 3 minus 4t. And z equals negative 2 plus 5t. And because this is a line segment, so same as our exam problem, t from 0 to 1. Okay, because we defined by this way. And we can try similar problem. So P is 1, 2, 3. Q, which is 0, 1, negative 1. Okay, just given any 2 points. And you can try this problem. I'm going to give you the solution. This is my PQ. Okay, so my points RT is given by this 1 minus t, 2 minus t, 3 minus 4t. Okay, I forgot to write down this back into vector function. So in order to write down vector function, it's better to write down this way. We should write down 1 plus t, 3 minus 4t, negative 2 plus 5t, because we are looking for the vector function. So for the exercise problem, same thing. So RT, I'm going to write down IJK form. So 1 minus TI, 2 minus TJ, plus 3 minus 4TK. Okay. Let's take a look at another example. Example 4. A little bit more complicated. Same thing, we want to find a vector function that represents the curve of intersection of x squared plus y squared equals 1 and plane y plus z equals 2. Okay. Firstly, I'm going to draw the graph to you, and then we find the parametric equations or the vector function for this one. So let's take a look at this one. Right now, let's take a look. Firstly, we can tell this is 3D problem because we have z here, right? Actually, we skipped the 12.6 in calculus 3. In calculus 3, we draw the graph of this x squared plus y squared equals 1. So in 2D, we know this is circle, but in 3D, it is we looked at as cylinder because we treated that in 3D means x, y satisfy the circle, but z can be anything. So we can say z can be anything. So that means cylinder. Okay, cylinder. So that's x squared plus y squared equals 1 means in 3D. In calculus 4, 12.6 is going to be the first section you are going to learn. So you will learn a lot of graph in 3D. And y plus z equals 2. So that means a plane. So here x, y, z. Okay. So actually, this is, for example, this is 1, right? Radius is 1. And here is like a plane. So it's a line in YZ plane, but you know x can be anything. So it's going to be a plane, kind of like this. And when we use the plane like a cut a cylinder, they intersect like kind of like this thing. Okay. So we are going to find the parametric equation or just the vector form for this curve. So I'm going to draw a graph. So we are going to find a vector function for this curve. Now let's take a look. Our intersection, the curve of intersection. So intersection means what? Means the curve satisfies both equations. So that means the curve satisfies both equations, right? Both equations. So the first equation means x squared plus y squared equals 1. So we can think about how about x equals cosine t, polar, and then y equals sine t. Okay, because we're going to use a parameter, right? Because we want to find a parametric equation. So like xt, yt, zt. So the best way for the circle is polar, x equals cosine t, y equals sine t. So we know that means x squared plus y squared equals 1. And we also want to find the z. Z equals what? So from here, you can see z equals 2 minus y, right? But in our parametric, they have to be x, y. They have to be all the function in terms of t. So like zt in terms of t. So we cannot have y here. So, but we can replace y by y equals sine t. Okay, so that is z. So z, we can find the function zt. Now, if we want to write down this as rt, going to be cosine ti, sine tj, and that z satisfy 2 minus sine t. Okay, or you can write down this cosine t, sine t, 2 minus sine t, component form, right? So that's the solution for this problem. You can see x, y satisfy the circle and z equals. Here I want to show you how to use computer to draw the graph. And this is my MATLAB. You can download MATLAB or you can just use the online version. I just like to use the online, so it's not going to take my computer space. And you can take a look here. We just make a t equals some, give t some value. So from negative 10 over pi to 10 over pi. So that's the t value. You can also make just negative t 10 to negative 10. So whatever you like, because it's like you can choose anything you like. Okay. And here this is function x equals 2 sine t, y 4 cosine t. So I can also, if I make this, so xy going to be a circle, right? And if I make that one, that means going to be ellipse. And the z equals to t. And right now we just run the graph. Give any name. Okay. So for example, let's see, we can say plot one vector function. Okay, so something wrong. Let's run this. Actually, this is the graph, the right side. Okay, so I'm going to run this again. You can see what's the graph look like. This look like helix, right? When z goes, it goes up. Okay, z goes up, and xy just satisfy the 2D equation here. And I'm going to post this code in OneNote, and you can just change your function.